The LIGO interferometer right now can detect when its 4-kilometer path changes its length by about 10 to the minus 18th meters. That's 1/millionth of a femtometer. And to give you an idea of what a millionth of a femtometer is, that's about 1/1000th the diameter of a proton. The Rational View is a weekly series hosted by me, Dr. Alan Scott, providing a rational, evidence-based perspective addressing important societal issues. Hello and welcome to The Rational View. I'm your host, Dr. Al Scott. On this episode, cool stuff, LIGO, the coolest experiment ever. So on this episode, it's a bit of a change of gear from my usual hard-hitting social commentary. I thought I'd try out a little piece on technology and science, just to whet your appetite on something you may not be aware of that you should know, because this is really, really cool. So please let me know, give me your feedback on whether you like this direction or not. I'll be back to more social commentary in follow-up episodes. So LIGO, what is it? It's a laser interferometer gravitational-wave observatory, and it's the coolest thing ever. LIGO can detect ripples in space-time, billions of light years away, caused by massive objects like black holes merging together as predicted by Einstein's theory of relativity. The two primary research centers of the LIGO Observatory are located at Caltech in Pasadena and MIT in Cambridge, Massachusetts. The detector sites are in Hanford and Livingston, and they're home to the interferometers that make LIGO an observatory. The European Union has its own system called Virgo, that it's operating in Cassina, Italy, near Pisa. Japan is building one called Kagra, the Kamioka gravitational wave detector, and India is also looking to build their own calibration with the LIGO team. Now, this has obviously been recognized. The Nobel Prize in Physics for 2017 was awarded based on the amazing discoveries put forward in this amazing technology. Gravitational-wave observatories have opened a new window on the universe. Now, if you like this content, please comment. Let me know what you think of it. If you don't like it, please comment and let me know, because then I can switch back to what you do like and share it with your friends. So, Albert Einstein originally predicted the existence of gravitational waves in 1916, about 100 years ago, on the basis of his theory of general relativity. Now, general relativity, as we know, interprets gravity as a consequence of distortions in a space-time continuum caused by the existence and presence of mass. Therefore, Einstein also predicted that events in the cosmos would cause ripples in the fabric of space-time, basically distortions of space-time itself, which would spread outward, although they would be so tiny and minuscule that they were thought to be impossible to detect by any technology foreseen at the time. In fact, Einstein made a statement that he said this would never be of use to science. Now, one case where gravitational waves would be strongest is during the final moments of the merger of two dense compact objects, such as neutron stars or black holes. Now, why would they collide? Well, over a span of millions of years, binary neutron stars and binary black holes lose energy through the emission of these gravitational waves, and as a result, they slowly spiral towards each other. At the very end of this process, the objects will reach extreme velocities close to the speed of light, and in the final fraction of a second of their merger, they will emit so much gravitational wave energy that, because of E equals mc squared, the energy and mass equivalency, this mass is converted into gravitational waves, and then they spread away at the speed of light like ripples on a pond through the universe, alternately stretching and compressing the fabric of space-time itself. So that's really cool. Now, as I said, these measurements were thought to be impossible. The measurement precision that you need exceeds 1 part in 10 to the exponent 21. That's a 1 with 21 zeros after it. And because this was unimaginable, Einstein said that this would never play a role in science. So that's why it's so darn cool. The LIGO experiment is based on a laser interferometer in the style of the Michelson-Morley experiment that was first built back in 1887. Of course, they didn't use lasers back then because there was no such thing as lasers. But they used filters and light sources, and they filtered the light so that it's a pure wavelength. That's the key thing you're getting from a laser in this experiment, is a pure single color. The purest single color that you can get is produced by a laser. It's a single wavelength, and the wavelength is related to the color of the light. So it's like a very pure color. And the reason this is important is that it moves through space like a wave, undulating up and down in electromagnetic fields. And the wavelength tells you the color, and it's based on the energy. And because it's moving through space in positive and negative directions, when two light beams come together of very similar energy or wavelength, then the peaks and troughs of the two waves can either combine constructively as positive interference, or destructively as negative interference, and cancel each other out. So if the waves are offset by half a wavelength, then nothing gets through to your detector, and if they're perfectly in phase, then it's doubly bright. And so the interferometer splits the light into these two perpendicular arms with mirrors on the end, and then brings it back together and combines it. And it's very sensitive to changes in the arm length. If you change the arm length just a little bit, then the train of waves gets pulled one way or the other, and the peaks don't line up anymore, or the peaks and the troughs don't line up anymore, as in LIGO's case. And this is how it detects distortions of space-time. And this is the idea behind the Michelson-Morley experiment back in 1887. They wanted to detect the changes in space-time as the Earth moved around the sun, because they thought that the Earth was dragging some sort of luminiferous ether with it, which is what the medium for light was supposed to be. We now know that this is wrong, and mainly based on their experiment that we found that there was no difference in the speed of light as Earth moved through space. So effectively, we know that the speed of light is the same in all directions. And as a result of this, Einstein came up with his theory of relativity, which showed that light is constant and space is what changes as you move faster and faster, which is really counterintuitive, and why he was such a genius, and the theory of relativity was so really cool. So the history of LIGO, just a little brief history. In 1967, Rainer Weiss demonstrated a laser interferometer with sensitivity limited only by photon shot noise. That's variations in the number of photons that are being emitted by the source, or detected by the detector in this case. And in 1972, he completed the invention of the interferometric gravitational-wave detector by identifying all the fundamental noise sources that a detector would have to face, and he conceived of ways to deal with them. And at that time, he showed, in principle at least, that these ways could lead to something that could detect gravitational waves from astrophysical sources. And before that time, as I said, people thought it was impossible. And then in 1968, Kip Thorne, another recipient of the Nobel Prize, created a research group at Caltech working on the theory of gravitational waves and their astrophysical sources, and later on the noise in interferometers. And they went on in the 1980s to the 2000s to formulate all the techniques for dealing with these things. And in 1980, the U.S. National Science Foundation funded the construction of a 40-meter prototype interferometer at Caltech, and Weiss's 1.5-meter prototype at MIT. And they further on funded Weiss to design and lead a technical cost study for the LIGO itself, a several-kilometer-long interferometer, which is what LIGO is now. In 1984, Caltech and MIT teamed up for the joint design and construction of LIGO. So this is quite a history. It's taken a long time, and in science, sometimes things take a while. It's not the same as the corporate world. You have long time frames to get these amazing discoveries, and you build and build and build. So the National Science Foundation in the U.S. reviewed the concept with a hard-hitting committee of experts and agreed that it really was feasible, and funding was then provided for a staged development to start with a simple LIGO and then upgrade to get to the sensitivities they thought they needed to detect the sources that had been modeled from astrophysical simulations. So using the initial LIGO interferometers, the LIGO scientific collaboration carried out a sequence of gravitational wave searches, partly in collaboration with the Virgo group in European Union, with ever-improving sensitivities. So in 2002, they started listening with their preliminary detectors with a sensitivity. It was only 1 part in 10 to the 19, only, I say, but that's really amazing. And then they kept working to improve it. And by 2010, they'd improved it by a factor of more than 1,000. And they didn't detect anything. So the first 8 years, they didn't detect anything. All they're doing is placing limits on, well, maybe this is nothing is louder than this in the universe in terms of gravitational waves. And that's got to be depressing, right? You've got millions of dollars that you've invested in this great big detector and just nothing. And that's part of science, right? They did this in a staged way to start out slow, to build up and address all of the noise sources that they expected to find over a period of years, and test them. And it's been a staged development, which I think makes a lot of sense. But still, way to go for sticking with it. And the prize at the end was good. So the LIGO interferometer right now can detect when its 4-kilometer path changes its length by about 10 to the minus 18th meters. That's 1/millionth of a femtometer. And to give you an idea of what a millionth of a femtometer is, that's about 1/1000th the diameter of a proton. Think about that. That is crazy. They've got a 4-kilometer long arm of an interferometer where they shine a laser down it, and they can measure when that arm changes its length by 1/1000th the diameter of a proton. Wow. If someone had told me you could do that, I would have laughed in their face. Until I saw it done, obviously. It would have been premature. So really good on them for sticking to it and getting there. So under development by MIT and Caltech since 1980, LIGO made its first detection of a gravitational wave in September of 2015. And this was groundbreaking, and this was amazing, and this was totally amazing. Took everybody by surprise, except for the people, I guess, who've been working on it for 30, 40, 50 years. Now, so here's the story. On September 14th, 2015, a series of gravitational waves from a distant galaxy first passed through the Livingston detector. Then just 7 milliseconds later, it passed through the detector in Hanford. The passing gravitational waves slightly altered the path lengths in the arms of both detectors by about 1/1000th the width of a proton. That slight change created a characteristic interference pattern in the laser light. And interestingly enough, this doesn't detect just fixed offsets. It can only detect oscillations. It has what we say a frequency range that it's sensitive to. So the creators found a range of frequencies where they could kill the noise sources, the sources of extraneous noise, enough that they could detect really, really well. So outside of this frequency range, they can't hear anything, really. And so here is an audio recording of the first discovery. A pair of 30 solar mass black holes colliding over 1 billion light years away. It sounds like a click, but if we boost the frequency just a bit, you can hear the chirp as the black holes spiral faster and faster, approaching the speed of light and stretching the fabric of space-time to its limit. Here it is. In the last few milliseconds, the gravitational energy emitted by this one event exceeded the total energy being emitted by all of the stars in the observable universe. And this massive exhalation of gravitational waves then rippled through space-time. the echoes of this massive collision spreading silently outward for over 1 billion years before passing through these two detectors on the Earth, to be detected as a wink of light in the most silent echo chamber ever designed. Based on the signal's amplitude, that is the height of the gravitational wave, team members estimate that the colliding black holes had masses of about 36 and 29 suns, respectively. Milliseconds before they emerged, these black holes spun around each other at nearly the speed of light. And LIGO was able to detect all three predicted phases of the collision: the black hole's death spiral and ensuing merger, as well as some ringing of the merged object as it settled into its new form, all predicted by Einstein's equations from 1916, if you'll believe. The merged black hole contains about 62 solar masses, so it's short 3 full solar masses from the initial black holes. And this mass all turned into gravitational wave energy through the E equals mc squared equation. So 3 whole stars worth of energy went to stretching the fabric of space-time. The measurements show that the source lies between 700 million and 1.6 billion light years away. Now, this tiny little blip in the recordings from LIGO needs to be assessed, whether it's noise or not, because LIGO creates data at a prodigious rate. It's listening for these very short clicks, effectively. So it's producing more than a terabyte of data every day. And based on the strength of the signal and the noise levels, that they are basically sure that this was an actual event. The chances of it being noise are less than 1 in 3.5 million. So it's a 5, in statistics, it's something we would call a 5.1 sigma event. And for all of this work and this discovery, the 2017 Nobel Prize in Physics was awarded to Rainer Weiss, Kip Thorne, and Barry Barish, who was kind of the leader of the LIGO technology building, for their contributions to the LIGO detector and observations of gravitational waves. So how do they do that? Let's talk about the technology a bit, because it's really cool. So first of all, you need a pair of perpendicular 4-kilometer-long evacuated beam tubes to form the measurement area. Now, if the relative path changes between these two perpendicular arms, it shows up as a signal on an optical detector or a photodiode. The system is designed to listen in a frequency range between 10 and 10,000 hertz, so it's really audible frequency ranges. And if you could have a big enough amplifier, which this is, you could hear it with your ears, which you just did. Interestingly, the LIGO Observatory also provides a proof that the Earth is a sphere. The curvature of the Earth over the 4-kilometer beam tubes, with a laser running down the middle, means that the ends of the tubes need to be boosted about 1 meter higher than the middle to compensate for the Earth's curvature. Now, 4 kilometers is actually not long enough to detect these tiny changes. If you had just a 4-kilometer long interferometer and you're detecting something 1/1000th the width of a proton, people would say, no, you can't do that. It's impossible. But what they do is they recycle the light. And so there's a resonant cavity in these arms that makes the light bounce back and forth down the path 300 times. So to the light that's traveling in the arms of the interferometer, it appears that it's not 4 kilometers, but 1,200 kilometers before they come back out and recombine to form a signal. And any error in the interferometer would cause the beam to distort and spread out and change phase. So they pump it down with a huge vacuum pump to 1 part in 10 to the 9th torr, which is basically 1/trillionth of an atmosphere of pressure. So it's like a almost perfect vacuum. And it's a 1.2 meter diameter beam tube, and it takes 40 days for the scientists to get all the air out so that they can operate it. So when they start pumping it down 40 days later, you got to make sure that everything's plugged in before you do that, because it would really suck if you had to then open it back up. Anyways, any vibrations from passing traffic, logging efforts nearby, even footsteps of scientists in the observatory need to be eliminated. the interferometer mirrors use inertia basically to stay in place and not vibrate. They're each 40 kilograms, the mirrors, very heavy mirrors, and they're suspended on the end of a passive vibration quad pendulum. And so it's basically four test masses hanging one from the other in this big pendulum of massive mirrors or massive objects. And this cuts the motion from vibration by a factor of 100 million. So that's pretty good. And it uses glass fiber wires to suspend the masses because metal wires have too much energy. If you know anything about the theory of electrons and metals, you would understand that. But effectively, they're using glass fibers to hold these things very stable. And this passive isolator is sitting inside of an active vibration damper, or hanging from an active vibration damper. So like noise-canceling headphones writ large. So the thing that mounts this thing is actively canceling all the vibrations it can, and then these four test masses hang below it on these glass fibers and vacuum chambers down. And oh my gosh, it's really cool. And so now the laser diode that seeds this interferometer spits out about 2 watts of infrared light. But that's not enough, and it has to be amplified, and it has to be frequency stabilized to be extremely pure to reduce noise in the measurement. So the laser output is frequency stabilized. They basically have a resonant cavity which they control the size of using a moving mirror on one end. And that ends up making a pure optical tone, similar to what happens when you blow across the top of a bottle and a note comes out. But this is light vibrating back and forth in a laser cavity. And this active stabilization increases the stability of the diode frequency by another factor of 100 million. And the laser power is then amplified with optical amplifiers and recirculating mirrors in the cavity to approximately 750 watts, which is a heck of a lot of optical power. If you know those little laser diodes, they're like, a few milliwatts at best. So this is 750 watts of light. It's just amazingly intense. And the laser mirrors then have to be wonders of engineering as well, because a normal mirror that you look at with a silver back on it is going to be absorbing a few percent of all the light. They're not perfect mirrors. Even the shiniest mirror that you have in your house is absorbing a few percent of the light. And if you were absorbing a few percent of 750 watts in your mirrors, boy, they would get hot fast and distort, and the laser beam would go all over to heck. So these mirrors are wonders of engineering, and the coatings on these mirrors are dielectric coatings. They don't use metal, they use dielectric, and the coating layers are made just so that they reflect the light backwards without absorbing anything. They absorb less than 1 out of every 3 million laser photons hitting them. So that's how they keep cool and don't distort. So now, that's the cool technology. Now you have the most sensitive echo chamber in the world. What do you do with it? Well, they ran their first 2 observing runs in 2015 and 2017, and in that period, LIGO spotted 11 merger events, 2 of which were also felt by the European Virgo detector during a few weeks in August 2017 when it was operating in parallel. The existing observations show that the merger rate of binary black holes lies around 50 mergers per cubic gigaparsec per year. Well, a parsec is another distance measurement, like about 3 light years. So, okay, that's great. So what? So with this observatory, we are now shedding light on the most exotic objects in the universe that many scientists 100 years ago did not believe existed, and even probably 50 years ago. Because the only way we can observe these is through their X-ray emissions from gas falling into them from nearby stars, up until now. And we didn't have a very good idea of their properties. We know that these things, major mega black holes, exist at the center of all the galaxies, or at least most galaxies. There's a mega black hole at the center, which is millions or even billions of solar masses. And we know that all large stars, like super large stars, many times the mass of our sun, will end their lives in a supernova, and their core will collapse into a black hole. or a neutron star. So this is all we really know about them. So we have theories, relativity and physics and things like this that tell us a lot about what to expect. But these observations help us to extend our understanding with real experimental data on extreme physics that many people didn't think we could ever do as a race. And this is amazing. So I want to tell you a little bit about some of the discoveries that have come in the last 5 years. So 5 billion years ago, in a galaxy far, far away, two huge black holes weighing in at 34 and 51 solar masses collapsed and merged into an 80 solar mass monster black hole. This event unleashed the energy equivalent of 5 suns in the form of powerful gravitational waves propagating through space at the speed of light. And on July 29th, 2017, these tiny ripples in space-time reached Earth, where they were detected by the most precise measuring device ever built by humans. That's the big one. On August 17th, 2017, LIGO and Virgo detected a unique 90-second long strong accelerating gravitational wave signature, very different from the 1 or 2 second long bursts previously detected from the black hole mergers. Virgo had been up and running for only a couple weeks at the time. On the same morning, astronomers monitoring the Fermi gamma ray satellite detected a short gamma ray burst, and this is something that astronomers had been detecting from time to time. And this burst was only 1.7 seconds after the collision measured by the gravitational wave detectors. So this is a link of gamma ray bursts to whatever this thing was. Using the time-measured delay between the gravitational wave signature of the pair of spiraling stars, they were able to triangulate the source of the gravitational signal and direct astronomers around the world to a small region of the Virgo galaxy cluster. Now, NASA's Swift X-ray transient telescope quickly slewed to the region but was unable to detect anything unusual. That night, however, astronomers were able to view the fading remnants of a visible explosion called a kilonova in the galaxy called NGC 4993. Great name. And this galaxy lies at a distance of roughly 130 million light years from us. What was this unique explosive event? Astronomers immediately recognized this as the death spiral of a pair of neutron stars with masses between 0.9 and 2.3 times that of the Sun. Now, neutron stars, as I said, are cores of collapsed stars that have been gravitationally collapsed beyond the electromagnetic forces that govern familiar matter that we see every day. The electrons that orbit each nucleus, because of the great pressure of the collapsing core, were forced into the nucleus and into the protons, neutralizing them, and ending up with a single huge city-sized pile of neutrons, like one city-sized atomic nucleus, if you will, weighing up to twice the mass of our Sun. Now, if they exceed about 2.2 solar masses, our theories suggest that even the strong nuclear force can't stop it from further collapse. And the strong nuclear force, of course, is the strongest force that we know of, and it's responsible for nuclear power. And so if it's more than that mass, then the neutron star would just keep collapsing and become a black hole, based on our theories. Now, the Las Campanas Observatory in Chile was the first to locate the 17th magnitude optical counterpart, so very dim. Astronomers were able to get good visible spectral data on the debris, and this clearly showed what the debris was made of because of the emission lines of the elements in the debris cloud in the explosion. They could see this stuff and compare it to lines in the lab, and it basically showed that it was littered with rare earth elements like gold and platinum. Now, we know from physics that supernovas create only sparse amounts of heavy elements like gold, platinum, and uranium. So the first time ever, astronomers had detected vast amounts of these things in the moment of their creation. So the neutron stars basically explode and create all these, they shatter into rare earth elements. And astronomers estimate that based on the intensity of the optical signals, that between 10 and 100 Earth masses of gold were created in this single explosion. And, of course, similar masses of other heavy elements. So, wow, this is amazing. From the data, we haven't been able to tell if there was a hypermassive neutron star or immediate collapse to a black hole from what was left. Only 16 binary neutron star pairs are known to exist in our entire galaxy. So, and because they spiral in at a known rate, we expect these explosions to happen only once every 10,000 to 100,000 years in our galaxy. So how is it that we heard one? Well, because of LIGO's extreme sensitivity, it can detect these out 650 million light years away. So it can listen to over 1 million galaxies like our own. And that's why it can hear neutron stars merging at the rate of several a year. And because we were able to detect both the gravitational rays and gamma rays for the same event for the first time, astronomers have now confirmed Einstein's prediction that they both travel at the speed of light to within 3 parts in 10 to the 15th. So it's an extremely precise measurement. And the amplitude of the gravitational signal gives us an independent measurement of the distance to the object, and we can compare this distance estimate to the measured redshift of the galaxy which it's in, which tells us something about the expansion properties of the universe. And astronomers estimate, based on this data, a Hubble constant, which measures the expansion rate of the universe, of 70 kilometers per second per megaparsec. So a completely independent measurement of the Hubble constant, which is smack dab in the middle of previous measurements. So wow, this is great and amazing and so consistent with all of our science. And it's really an amazing thing to be alive in this time and to see all this stuff. So after this, all 3 of the gravitational wave detectors were upgraded for a new simultaneous observing run called O3 that started in April of 2019. And they've been flagging detections approximately once a week with their improving sensitivity. And in this particular observing run, the astronomers have used some really cool physics. They've gone to quantum physics to improve the sensitivity of the detector. They've used what they call quantum mechanically squeezed photon states in their laser to double their sensitivity. And quantum mechanical squeezing is really cool, and I don't have the time to do it justice here, but just suffice it to say that it exploits the Heisenberg uncertainty principle. And Heisenberg uncertainty principle tells us that when we measure one property of a system very accurately, we lose accuracy on another coupled aspect of that system. So if we measure the position of something very accurately, its momentum becomes wildly uncertain. So in this case, they're squeezing the properties of the laser beam to make a much purer tone, but allowing the intensity of the beam to fluctuate a little bit more. So they're using a crystal that tricks the beam into having an extremely pure tone, and that actually doubles the sensitivity of the whole thing, because we're looking at phase changes in the waves that are oscillating down the arms of this interferometer. So using the upgraded detectors, astronomers have been detecting more and more events, including lighter black hole mergers that they couldn't detect previously. And in fact, on the 12th of April 2019, they detected an interesting gravitational wave hum that had a higher harmonic to it, similar to like the overtones you get in musical instruments. And this is indicative of a system with highly unequal masses. They had the black hole masses were 8 and 30 times the mass of the sun. And this allows them to determine precisely several other properties of the system: its distance to us, the angle we're looking at, how fast the black holes spin on their axis, which is another interesting relativistic effect that people wouldn't expect you might be able to detect. And analysis revealed that the merger happened at a distance between 1.9 and 2.9 billion light years from Earth. And there are several more discoveries from O3 that have yet to be published, so stay tuned for more. So thank you very much for listening to this. I hope you enjoyed it. For me, it was a lot of fun researching it because I just love the experiment and the physics and the cosmology and all that we're learning right now. So thank you very much for listening and tuning into The Rational View. If you're enjoying what you're hearing, please consider visiting my Patreon page and becoming a patron of this podcast. at patron.podbean.com/TheRationalView.